The Constitution of India, Preamble. We, the people of India, having solemnly resolved to constitute India into a sovereign, socialist, secular, democratic republic and to secure to all its citizens justice, social, economic and political, liberty of thought, expression, belief, faith and worship, equality of status and of opportunity, and to promote among them all fraternity, assuring the dignity of the individual and the unity and integrity of the nation. In our Constituent Assembly, this 26th day of November 1949, do hereby adopt, enact and give to ourselves this Constitution.
Happy morning, students. I hope you all are now enjoying your classes because you come to school as just like our regular school periods and you are attending the classes now. So I hope you will be happy, energetic because you are in your own school campus, getting a positive energy from everywhere, right? So we will be moving into further classes with the same energy and try to achieve the maximum that is possible from us, right? So today's class we are going to focus on the new topic, enthalpy. Last class we were learning about the work done by the system, on the system, or heat transferred into the system or from the system. So today we are going to learn a new topic which is enthalpy, which is nothing but heat energy. Now which is denoted by a symbol H. As we already know, del U is equal to QV, which is a constant volume, the internal energy or the heat absorbed at a constant volume. But in most of the cases, if you see any transformation that is happening, it may not be happening in a constant volume, but it can take place even at constant pressure. So that is the most possible situation. At that we can write del U, which is Q plus W, as del U QP minus P del V, where QP is the heat energy and P del V is the change or the work done at a change in the volume at constant pressure, which is the work done on the system. So let us consider two states of a system, initial state and the final state, because as I told you in thermodynamics, the whole process takes place considering the initial and the final states of the system. So here let me put 1 and 2 subscript as initial and the final states of the system. So change in internal energy U2 minus U1 will be equal to QP minus P into V2 minus V1, which is change in the final volume minus initial volume. Now if I am going to rearrange the equation, I will take the QP on the other side, U2 plus PV2 minus U1 plus PV1, which will be equal to the heat energy. Now let us define the term enthalpy now. We know enthalpy is nothing but sum of internal energy plus the pressure volume, U plus PV. So if I am going to substitute U plus PV as enthalpy, I get QP will be equal to H2 minus H1, which is nothing but the change in the enthalpy, that is del H. So I will again write del H is equal to del U plus P del V, and we know del H is nothing but QP, which is del U plus P del V. Now this del H, that is the change in enthalpy, it can be of two types. One is exothermic, when heat is given out from the system to the surrounding and it will be negative, and del H is positive if it is endothermic, when heat is taken from the surrounding into the system. When heat is absorbed by the system, it becomes positive. So in a condition where del V will be equal to 0, del U is equal to QV, which is the change in internal energy at constant volume. Now this happens only in the cases of solids and liquids. If you consider solids and liquids only, the change in volume affects a lot. But if you take gases, it does not affect a lot, but when you consider gases, the change in volume, it matters a lot, because gaseous state you cannot define it properly. So now we are going to see, using the ideal gas equation, how a change in volume can affect it. So now let us consider, I told you, a change in volume with respect to gases. So what happens here, if VA is considered as the total volume of the gaseous reactant and VB is the total volume of gaseous product, NA number of moles of gaseous reactant and NB number of moles of gaseous product. Now we know, according to ideal gas equation, PV equal to nRT. So PVA will be equal to nART, where pressure is constant, temperature is constant, R is a gas constant. So PVB is equal to nBRT. Now when I take pressure as common, VB minus VA will be equal to NB minus NA into RT. Now if I am going to rearrange, P del V is equal to del NG RT. What is del NG? It is nothing but the difference between number of moles of gaseous product minus number of moles of gaseous reactant. Now when you substitute the value of P del V, which is del N RT, in this equation of enthalpy, we get enthalpy is equal to sum of internal energy plus del Ng RT. So this equation you will be using in your problems, which is important, which we will be discussing when you are in the class with me directly. Now, so this is the derivation for the change in enthalpy. Now this enthalpy plays a very important role, because when we were dealing about the state variables like temperature, pressure, volume, heat capacity, or when I say mass, anything, there are two types of characteristic property. One is called as an extensive property, the other one we call it as an intensive property. When I say extensive property, these are the particles or these are the variables whose value depend on the quantity of size or matter. Those are called as extensive, mean they depend on the matter, they depend on the size. The size changes, they change. If the matter quantity changes, they change. So those are like mass, volume, enthalpy, heat capacity. These are the examples of the variables or the properties which show extensive character. When I say intensive property, those they do not depend on the change of size or matter. Now they are like temperature, density, pressure. Now how can you verify this? Let us consider a container in which gas molecules are present inside. It has a particular volume and temperature. Now what happens if I am going to divide, that is I am going to partition it, I am going to divide into two containers. One container I am going to separate into two. So what happens to temperature inside the container? It remains the same, it does not change. But what happens to the volume? It becomes half. That is, the whole container has turned into two halves. So what happens here? Volume becomes an extensive property and temperature becomes an intensive property. Any change in the size of matter has not affected temperature, but it has strictly affected the volume. So these are called as extensive and intensive property. Now we will be learning about heat capacity. Now let us learn about a new term, which is heat capacity. Heat capacity. What does capacity means? The amount, that is the ability, how much heat can be transferred to the system. So we are going to learn about the heat transferred to the system. So we know when temperature increases, that is nothing but heat is absorbed by the system. This is a system, surroundings is there. So this system is going to absorb some heat from the surrounding. So the temperature gradually increases. So increased temperature will be proportional to the heat transfer. How much ever heat is being transferred from the surrounding into the system, there will be an increase or rise in temperature, which can be written as Q, which is the heat transfer coefficient into delta T, because this is Q is proportional to del T. To remove this proportionality constant, you put a coefficient. This is nothing but magnitude. The coefficient magnitude depends on the size, composition and nature of the system. What type of system it is there? what is the content matter it has got and what is the size of that system. Everything is dependent on C, which is called as a heat capacity. So if C becomes more, the temperature rise will be less because C is equal to Q by del T. These two are inversely proportional. So for water, if the heat capacity is more, which means so much heat should be given out to increase the temperature of the system. That heat capacity is proportional to the amount of substance, which I told you the composition. So Cm, which is the molar heat capacity, will be given as the heat capacity with respect to 1 mole of a substance, where N is 1 mole. So specific heat capacity is nothing but the quantity of heat required, that is the amount of heat which is required to increase the temperature of 1 unit mass of a substance by 1 degree Celsius or 1 Kelvin. That is called as a specific heat capacity. So Q will be Cm del T, C into M, which is nothing but our C, which is our heat capacity. So Q will be equal to C into del T. This is the value for the finding out the heat capacity, because if heat capacity is known, we can directly find out a rise in temperature. So with this now, what is the relation between Cp and Cv, that is constant pressure and constant volume. See, at constant volume, the heat capacity is given as Cv. C is the heat capacity at constant volume. At constant pressure, the heat capacity that is given as Cp, which is heat capacity at constant pressure. So constant volume, Q can be written as Cv del T. You remember children, Q is equal to C del T. So constant volume del T, which is nothing but del U. We also know that del U is equal to C del T, which is QV. That is constant volume, the heat energy transferred will be equal to the internal energy. Now at constant pressure, Qp is equal to Cp del T, which is nothing but del H, because del H is equal to Qp. Now we are going to find the difference between Cp and Cv. So Cp minus Cv, how can you do that? We are going to do for ideal gas equation. That is, for any ideal gas, for 1 mole of an ideal gas, del H is equal to del U plus del PV, because it can be P del V or del PV. Similarly, which PV is equal to RT. So del U will be equal to del RT. Here I am substituting, instead of PV I am writing RT. So R is a gas constant which will never change. So del H can be given as del U plus R del T. This will be my main equation, R del T. Now what I am going to do? In the place of del H and del U, I am going to substitute Cv del T and Cp del T. So Cp del T is equal to Cv del T plus R del T in this equation. What is del H? Cp del T. What is del U? Cv del T. So Cp del T is equal to Cv del T plus R del T. Cancel all the del T. You get Cp equal to Cv plus R. Cp minus Cv is equal to R, which shows the difference in the heat capacity at constant pressure and volume will be equal to the universal gas constant. So this is a heat capacity. Next, we have two important methods, though it does not come in the exam often, explaining the calorimeter for finding out the heat capacity. I will be posting 2 videos with respect to the calorimeter experiment. So you can check in page number, children, 169. Measurement of internal energy using a bomb calorimeter, and you have measurement of enthalpy using again a calorimeter, which I will be posting 2 videos for you to understand how this experiment works. Now we will get into enthalpy change for the reaction enthalpy. Enthalpy change, that is reaction enthalpy. That is any enthalpy change that is taking place during the course of a reaction. Any enthalpy change, which is nothing but the heat change that is happening during a particular reaction, we call that as reaction enthalpy. Now how does it takes place? Given any reaction, you find the reaction enthalpy by sum of the enthalpies of product minus sum of the enthalpy of reactants, that is product minus reactants, will be giving the enthalpy change for a reaction. So we write it as summation I AI enthalpy of product minus summation I BI enthalpy of reactants, where this sigma refers to the summation, sum of all the product, sum of all the reactants. AI and BI are the stoichiometric coefficient of product and reactants. So let us consider an example where we have combustion of methane. CH4 plus 2O2 gives CO2 plus 2H2O. I have written here gas, gas, gas and liquid. These are the state at which that particular molecule is present. So reaction enthalpy is given as summation of product minus summation of reactant. So HM, which is my molar enthalpy of product now, carbon dioxide in its gaseous state plus 2HM, that is 2 molecules of water. So 2HM of H2O in the liquid state minus, now reactant I should write HM, that is 1, stoichiometry is 1, HM of CH4 and GM plus 2 HM of oxygen at the gaseous state. So this will be my enthalpy of a reaction. This enthalpy of reaction is very important to study the changes that is taking place in a reaction. Now we will be learning some standard enthalpy changes taking place in the reactants, transformations and other thermochemical reaction. So today we will be learning about any 2 or 3 enthalpy changes and then we will go for the further reactions. Now we are going to see some of the enthalpy changes, that is I told you when we are studying about the enthalpy of a reaction, we have standard enthalpies of reaction. What do you mean by standard enthalpy? When I say standard, it has a specific standard of a particular molecule or a particular reactant or a particular product. So it is the enthalpy change when all the participating substances are in their standard state. So what does standard state means? It is a standard state of a substance at a specified temperature is its pure form at 1 bar. At 1 bar of atmospheric pressure, what is the particular temperature? That will be the standard state of a substance. So the pure form, say ethanol, when I say at 295 Kelvin or 298 Kelvin, it will be a pure liquid at 1 bar. So that 1 bar, it behaves as a pure substance. That is called as a standard state of a substance and it is denoted with a symbol dash putting a circle around it. So when I write standard enthalpy change, I put del H. On the superscript, I put a symbol dash, hyphen and a circle. So first let us learn about enthalpy change of phase transformation. What do we consider here in phase transformation? We have mainly focusing on 3 states of matter, solid, liquid and the vapor phase. So here we are going to see how the phase changes from one form to another form. So let me consider first melting of a solid, that is ice into a liquid. So here the phase transformation is from solid to liquid. So considering water solid, it melts to become a liquid. That melting process is an endothermic process, which means there is an intake of heat, absorption of heat. So del H, that is the enthalpy of fusion, which is a transformation of a solid phase into a liquid phase, which is an enthalpy of fusion denoted by del fuse H with a standard symbol which is 6 kilojoule per mole, which will always be positive because it is an endothermic reaction. So enthalpy of fusion will always be positive since it takes with an absorption of heat. Next, let us consider the phase transformation from liquid to vapor form. So here a water liquid is getting converted to vapor form. Again we know when it is being heated, when it absorbs temperature, there will be a vaporization taking place. So that process we call it as enthalpy of vaporization, which will be denoted by the symbol del vaporization H to the standard state. It becomes 40.79 kilojoule per mole. The last one is enthalpy of sublimation. Here the solid is going to get directly converted into vapor phase. There is no intermediate liquid phase formed. Let us consider two examples. Solid carbon dioxide, it gets converted into the vapor form at 195 Kelvin very fastly, and the energy, that is the enthalpy change of sublimation, is 25.2 kilojoule per mole. But in case of naphthalene, you know what are naphthalene balls? We use in our cupboards to get a good fragrance or to avoid moths and repellents, right? So there naphthalene gets converted into the vapor phase, but very slowly, and the enthalpy of sublimation is around 73.0 kilojoule per mole. So these are the different enthalpies of phase transformation: enthalpy of fusion, enthalpy of vaporization, and enthalpy of sublimation. So with this, I think we will stop the class. We have some problems which we'll be doing in the class when you come here. So the rest of the topics, enthalpy of formation and other things, we'll be seeing in the next video. Thank you, children. With this, I'll be posting 2 videos as I told earlier. So watch the videos, and if you do have doubts, please don't hesitate to ask me. Thank you, children. Take care. Bye. Enthalpy and calorimetry. The changes that are happening in the surrounding atmosphere, everything happens at a constant pressure. These changes which are accompanied by the constant pressure is what we are going to learn as enthalpy. Any change happening between the system and the surroundings happens with the involvement of heat. It can be absorption of heat or it can be evolution of heat. So this absorption and evolution of heat is called as enthalpy change, which are exothermic and endothermic reactions. So here we are going to learn about the mechanism which is involved, which is called as a reaction enthalpy. At a constant volume, internal energy will be found out, which is the change that is happening between the system and the surroundings. Now, the change in internal energy by work done on the system or by the system will be depending on the state variables volume, temperature and pressure. So, delta represents a state function and not as a path function, but the heat and the work will be depending on the path function. So here del H is equal to del U plus P del V. So the internal energy can be found out, and P del V is the change in the volume with respect to constant pressure, which is a work done by the system or on the system. So change in enthalpy depends on the initial and the final states, so which is a summation of energy of product minus reactants. Now this change in enthalpy is done with a change in volume, which is the initial and final volume. So H1 and H2 can be found out. So del H will be H2 minus H1, which is U2 plus PV2 minus U1 plus PV1. In this case, U2 minus U1 can be written as del U, which is a change in enthalpy, and P del V will be the work done at constant pressure with a change in the volume, which is the enthalpy change, that is del H. Del U, as we all know, it is a addition or sum of Q plus W. So Q will be the heat energy and W will be the work done on expansion. So it is represented as minus P del V. Now del U is Q minus P into del V, and del H is equal to Q minus P del V plus P into del V, substituting the value of del U from the last equation. So here the internal energy, which is a sum of Q plus W, can be heat gained or lost by the system, and W is the work done. In an open system, if Q is positive, it means the system gains heat, and if it is negative, the system loses heat. and the work done, if it is negative, work done by the system, and if it is positive, it is work done on the system. So the total of the plus and the minus will be giving the del U, which is the internal energy, which means positive if the net gain of energy is by the system, and it is negative if the net loss of energy from the system. So calorimetry. Now we need to know the heat, that is the amount of heat which is being exchanged between the system and surroundings. The science of measuring the amount of heat is called as calorimetry, which will help us to learn about the amount of heat which is being exchanged between system and surrounding. So it can be transferred from system to outside surrounding or from the surrounding to the system. This is a setup of a calorimetry which is used to measure the enthalpy change for a system at constant pressure. So the heat capacity C can be determined if the mass m and the molar mass of the substance capital M and the temperature difference del T, which is a rise in temperature, is known. So del H is equal to del Q, which is equal to m into C into delta T. In the open system, the energy exchange takes place with the internal energy. If it is endothermic, the system absorbs heat, and if it is exothermic, the system releases heat, which will be negative. I hope, children, you are able to understand the exact amount of heat that is being transferred into the system. Bomb calorimeter. Bomb calorimeter is a device which is used to measure the heat exchanges associated with chemical reactions, specifically combustion reaction in which oxygen support is required. This is a setup of a bomb calorimeter, which is depending on the principle that heat gained by one body is equal to heat lost by another body. It consists of 3 concentric layers, in which the first layer will be an insulated layer, which will be made up of an insulated vessel which does not allow the heat interference from the surrounding to the system. The second one will be a bucket which is filled with water that is kept inside the first layer, which absorbs the heat that is transferred from the system to the outer layer. There will be a thermometer which is placed inside to note down the rise in temperature, and also a stirrer is placed to maintain the uniform temperature. The third layer consists of a small bomb, a smaller sealed steel chamber which is called as bomb, in which the substance to be heated is placed inside. To this bomb, there is a nozzle which is placed inside through which the oxygen is supplied. The whole setup is connected to through electrical leads in which the current is supplied so as to start the combustion reaction. So when the substance gets heated up, the chemical bonds are broken and the heat energy is supplied. This heat energy release can be calculated using the thermometer, and now this is helpful to find out the heat absorbed by the water or the heat generated by the substance using the equation Q is equal to, where we have already studied, ms del T. So in this, m will be the mass of the water, s will be the specific heat capacity of the water, and delta T is the rise in temperature. Thus, we can calculate the Q value using bomb calorimeter. It is also useful to calculate the calorific value of substances like wood, crude oil, charcoal, and also the calorific value of food content like any food that is being given to us. Summary. A bomb calorimeter measures the heat exchange during combustion reactions. It can be used to measure the calorific value of foods.